Now the third component is very important in scale technologies, because leakage current, as we discussed many times, is going to happen across all the billion transistors in the circuit. But more importantly, this is not a transient phenomenon, it's a steady state phenomenon. So even if you slow down your clock and try to make your dynamic power lower, right? For example, if you look at this, right, if you look at the transient power is equal to P dynamic plus short circuit, you will get this to be alpha into F clock into CL VDD squared plus IP into VDD minus 2 VTN into T rise, right? Now if I want to reduce the total transient power, one way is, of course, I can reduce my VDD square, VDD actually, right? Therefore VDD square will reduce, dynamic power will come down, and of course dynamic power is going to be the dominant component of this transient power compared to short circuit and dynamic power, right? This will dominate. But beyond a point, I cannot keep reducing my supply voltage. There are certain limitations in scaling the supply voltage also. So therefore, the best way is to actually reduce your frequency of operation also if you want to make the power lesser, right? You can reduce F clock to reduce P transient. This is a very effective way, right? Unfortunately, you should be very careful of this, because the next component of power that we are going to talk about is going to happen only in the steady state. So if you slow down your clock and give more steady state period to the clocks, then you are going to leak more and more amount of leakage power at that time, right? So this is the leakage power is like this. So if my input is 0, output is VDD, right? In which case the NMOS is on and PMOS is off. On the other hand, if my input is 1, output will be 0, right? The NMOS will be on and PMOS will be off, right? So therefore, the on guy is going to connect you to the supplies, either VDD or ground. So who's the guy who's going to leak current when the input is 0? It's the NMOS transistor that is going to leak current. So you have high NMOS when the input is 0. Similarly, when the input is 1, I have high PMOS that's going to leak, right? So if I look at my switching here, let's say my input switch is like this, V in, V out, right? Then during this period, I am going to have all the transient power. During this period, here, I am going to have steady state power, right? And also here. And if you take a slightly slow clock, effectively it's the entire clock period during which you are going to have this leakage current. Okay, this is also P steady. So what is the power from VDD in steady state? It is VDD into, it's just VI. Steady state current is I NMOS or I PMOS, right? This is I NMOS, right? Or it's going to be VDD into I PMOS. Okay, I'm matching the color in all of these diagrams. Okay, so therefore I can say, maybe I can say average power is VDD into I NMOS plus I PMOS by 2, okay, across the entire cycle, right? So unlike dynamic power or short circuit power, this does not depend on the clock frequency power. But if I ask you what is the leakage energy, then I have to tell you for how long, because it consumes this much power, and if I multiply it by the time, then I will get the total leakage energy. Okay, so one is dominated by energy, the other is dominated by power, right? And you must keep this in mind always. Okay, so now the question is, what is this equation, by the way, I NMOS and PMOS, right? It's going to be some W by L I naught e power VGS minus VTN by N phi t into 1 minus e power minus VDS by phi t. Okay. So question is, fine, I do have leakage power, right? It exponentially depends on all these parameters and so on. How do I reduce this leakage power, right? Because remember that this is the guy that's going to kill your battery. Your phone is doing nothing, but still there is power being drawn from the battery. So when it is idle, if I can do something to just reduce this power, it's going to be very, very helpful. Okay, and that is what is known as stacking effect. Okay, so let me show you this. Sorry, no, it's not PMOS. 0. Which amongst these two do you think will have lesser leakage current? So this is slightly an incomplete question, because I have to tell you now what the widths are, because I just showed you that in the previous expression it also depends. Larger the width, it's going to leak more current, right, and it's going to go linearly. So therefore let me say that this is W, right, this is W and this is also W. Now amongst these two, which ones do you think, which one is going to leak lesser current? Yeah, A, B. Huh? A or B? A will have higher leakage. Why? VDS is okay. So good, you are getting there. So let us first of all try to evaluate what this leakage current is in the ideal case. Okay, I am going to consider now an ideal transistor, slightly differently defined from what I used to call an ideal transistor earlier. Ideal transistor earlier was no leakage current. We had only the, the V-min model, linear saturation, velocity saturation, and then I off was 0. Now I am saying, okay, this is an other kind of ideal transistor where I have no short channel effects. Okay, let us assume 1, no body effect. Okay, we'll come to all this later. Let's assume that means gamma is 0. 2. No dibble, no drain induced barrier lowering. That means with VDS my VT does not change. Okay, so eta is equal to 0, right? Now we can evaluate what the leakage current through this stack is. Of course, this is a single stack, one stack, and this is a two stack. So how do I evaluate the leakage current through that stack, right? What you do is you have to assume that this is going to be this transistor. Let me call it N1, N2. Current through N1 is I1, current through N2 is I2. What is the constraint? I1 has to be equal to I2. Okay. So what is the value of I1 from the previous equation? W by L into I naught. What is VGS of the first transistor? Yeah? No. Okay. So N1, N2, VGS, VDS. First tell me what is the VDS of, let's assume that this intermediate node is Vx. So what is VDS of N2? Vx. What is VGS of N2? What is VGS? 0. Gate is grounded, source is also grounded. N1 transistor, what is VGS? Minus Vx. VDS, VDD minus Vx. Okay. Now first, to simplify our evaluation, we have to make some, get a feel for what this Vx will be. Will it be close to ground or will it be close to VDD? First of all, close to, why? No, leakage current will be less is not something that it will fix Vx so that the currents match, that's all. Whatever current you get, you get. So since I1 has to be equal to I2, right, the VGS and VDS have to adjust itself for both transistors so that the two currents are the same, correct? So if you look at N2, VGS is 0. Compare it with N1, Vx is some value between 0 and VDD. I don't know what it is, we have to figure that out. If Vx is even 100 millivolt, right, VGS for N1 is minus 100 millivolt, it's actually lesser. That means because of VGS, N1 can permit much lesser leakage current already, correct? N2 can permit much higher leakage current because VGS is 0. So now tell me, will Vx be close to ground or Vx be close to VDD? So N2 has large VGS compared to N1. Compared to N1, N2 has large VGS. N1 has small VGS, right? This is minus Vx, 0. Now if both currents have to be the same, the VGS has to be compensated by the VDS. Only then you can have these two currents to be the same, correct? You agree with me? So if N2 has a large VGS, then VDS has to be small. How will N2's VDS be small? Vx is close to 0, right? So implies VDS is small. Therefore, right, now here N1, since VGS is small, implies VDS is large. So if Vx is somewhere close to ground compared to VDD, that is, right, then these two will easily match. So conclusion, Vx is closer to ground, and assume third assumption, VDD is large. Okay. So now let us write down these current equations. I1 is going to be, or let's write I2 first because it's easier. I2 is W by L I naught e power, what is VGS? I2. Look at this table, 0, right? So it is minus VTN by phi t. I am going to make one more assumption, ideality factor N is 1. Let's assume that you are able to manufacture the device so well so that the subthreshold slope is really minimum and all that, okay, all that, no issue, right? Into 1 minus what? Vx by phi t, correct? What is I1? E power VGS is minus Vx minus VTN, okay? This is where assuming that the body effect coefficient is 0 helps, because for N1 the source is not at 0, its body here will be at 0, therefore there is going to be a body effect that will come in there, but for initial, just to give you the intuition, I am now assuming body effect is also absent, right? So therefore both VTs will be the same, Vx minus VTN by phi t into 1 minus e power minus VDD minus Vx by phi t, but Vx is close to ground, so therefore I can just make that 1 minus e power minus VDD by phi t. Now VDD is large enough, which means it should be greater than 3 times phi t. What is phi t? 26 millivolt at room temperature. So if you are over 100 millivolt, which VDD for sure is, right, you can neglect that 1 minus e power minus VDS by phi t, right? So I am going to just say this, okay? So now I wanted to equate these two currents and find out what that intermediate node voltage Vx is. Phi t? Now, so cancel everything, implies Vx is phi t ln 2. Now tell me what will happen to the leakage current I1 or I2 if I substitute this value in. What is I1? Yeah? 1 by 2 W by L into I naught e power minus VTN by phi t. Okay. Now let's go back and you tell me what is the leakage current through this guy. Let me call this I 1 prime. What is I1 prime? What is I1 prime? What is VGS for this transistor? 0. What is VDS? VDD. So I can clearly write I1 prime as W by L into I naught e power minus VTN by phi t. Correct? What this is telling us is putting two transistors in series is simply giving me the effect of halving the width. Correct? Vx has gone and adjusted itself at phi t ln 2 so that the leakage current through the 2 stack NMOS transistor is half that of the single NMOS transistor with the same width W. Okay, so this actually is not stacking effect. If I put two transistors in series, right, for example, if I put two transistors in parallel, right, and I do something, this is like one resistance, this is like another resistance, parallel resistance is R by 2. Similarly, series resistance is 2R, which means it's like halving the width in general, right? This is not the actual stacking effect. So what I wanted to show you here is, if I don't consider all these short channel effects, leakage current is not going to come down drastically, because what it's saying is, now instead of this guy, I will simply use a transistor like this, because even when you consider delay and other things, that is exactly what it is. It's going to result in a transistor with W by 2. This is equivalent completely with respect to delay and everything. So why will I even go and add the extra transistor, make it more area, more this thing, and then get the same leakage current? It's not beneficial. What happens is, because of short channel effects, for example, now consider dibble. The bottom transistor Vx is very close to 0, right? So the dibble effect is extremely less there. The top transistor VDD minus Vx is going to be very high, right, and it's going to be close to VDD, right? So what will happen to the threshold voltage of that transistor there? Yeah, it will reduce, correct? So these two fighting will actually cause a significant reduction than just having that VDD. So what happens is, because my top, if I consider, okay, let me write that down. I think I cannot just talk through it. Okay, now with dibble, single NMOS transistor is like this, right? VDS is just VDD, right? So the dibble effect on VTH is equal to eta times VDD. Now here, when I consider two transistor stack, 0, 0, right, VDD, the dibble effect on the top transistor, right, is VDD minus Vx. On N1. N1 is equal to eta into VDD minus Vx, right? Since that is lesser, if you consider the VTN of this transistor here, it will be lesser by eta times VDD. Whereas these two transistors, now they will not have the same VTN, of course, because of dibble, right? The two transistors N1 and N2 will have a different VTH, but will also be higher than the VT of this single NMOS transistor. Okay? So what I'll do is, since we have run out of time, please think about this and come back. Just stacking two transistors does not give you the needed impact. right? That's not why people have used this technique so effectively. That's what I wanted to show you through that derivation. Ideal case, it just reduces to a half the width transistor's leakage, which is useless. I might as well use a transistor, single transistor with W/2 and get the same effect, right? It's because of short channel effects that you get much more of a benefit in through the stacking effect. So I would even urge you to do a simulation now, right? You can go with your simulator LT Spice, put a single transistor, put a double transistor, see how much of reduction you're getting in current. Of course, put the appropriate W's and see. You just see, you will find that it's much more than just W/2. Okay, I'll explain that in the next class.